Logistic growth part 1. What logistic growth is with a solution. Before we get to logistic growth, let's talk about exponential growth or unlimited population growth. The statement that gives this type of growth is the rate of change of a population y with respect to time is proportional to the population itself. If we were to solve this differential equation, we would first separate the variables. You may want to watch the video on separable differential equations if you have not already done so. And then integrate both sides. The left side would give us the natural log of y. The right side would give us kt plus some constant of integration c1. Doing e to both sides, we would get y equals e to the kt plus c1. Using properties of exponents, that will give us e to the kt times e to the c1, where this back part is some unknown constant. So the solution would be c e to the kt. And if k is positive, we have exponential growth. The graph is shown on the left. This is a pretty typical model of population growth, but it assumes that population can grow forever, which is not necessarily the case. Instead, we think that population is limited perhaps by resources. For example, if you had grizzly bears in a nature preserve, that preserve could only sustain a certain number, which we call a limiting factor L, of grizzly bears. Turning our statement into a differential equation, we get that the rate of change of a population with respect to time varies jointly as a product of the population and the difference between the population and a limiting factor L. We are going to solve this differential equation in this video and not really do much else, and you will see why in just a bit. Now, this is a separable differential equation, so let's go ahead and solve this one. I'll move everything or every factor that has a y to the left side and isolate the rest on the right, and then we want to integrate. The technique to integrate the left side is partial fraction decomposition, which is also shown in another video. So I will give the highlights of that. We're looking strictly at the integrand on the left side without the dy, where it can be rewritten like this: a over y plus b over L minus y. Finding a common denominator, we would get a times L minus y plus b times y equals 1 over a common denominator, which we can ignore and just solve across the top. If I were to choose y equals 0, we would get a times L equals 1, or a equals 1 over L. Choosing y to equal L, we would get a times 0 plus b times y. Let me fix that really quickly. B times L, because y equals L, equals 1. which would give us b equals 1 over L as well. Therefore, we can rewrite our integral as 1 over L, and I'll just factor it out because a and b both equal 1 over L. 1 over L times 1 over y plus 1 over L minus y dy. You may want to stop the video here and take a look to make sure that you can get that left side. And then the right side will give us k dt. Now remember, L here is a constant. It's some sort of limiting factor. It is the greatest population that could exist in that whatever, that area preserve or whatever we're talking about. Now I'm going to multiply the 1 over L to the right side. I'll put it right here and I'll cross it out on the left side. On the left, we would get natural log of y plus natural log of L minus y times -1. This -1 comes from the fact that we would need to do a u substitution on that second part, equals KLT. K times L is a constant, so the antiderivative would be K times L times T, plus some constant of integration C1. Again, pause the video if you need to make sure you agree with every piece of that line. Now, we're going to do some algebra. It's going to take a little while because our final goal is to solve for y. That is, get y alone. What does y equal? I'm going to rewrite the left side as natural log of y over L minus y using properties of logs. And just rewrite the right side. We do e to both sides, gives us y over L minus y equals e to the KLT plus C1 like that, which we could write as e to the KLT times e to the C1, or C2 times e to the KLT. Now, we still got to get y alone, so we have a bit of algebra to do left. I'm going to put y equals, and then I'm going to multiply this bottom factor to the far right over here, giving us L minus y times C2 e to the KLT. Then we can distribute, giving us L times C2 e to the KLT. I'm not going to make L times C2 a separate constant. We'll see why in a bit. Minus y times C2 times e to the KLT. And now we can add this piece to the left. As stated, lots of algebra. Giving us y plus y times C2 times e to the KLT equals L times C2 to the times e to the KLT. Factoring out a y on the left, we get y times 1 plus C2 times e to the KLT equals L times C2 times e to the KLT. And then dividing. Y equals L times C2 times e to the KLT over 1 plus C2 times e to the KLT. And you would think we would be done. but we're not. Instead, let's factor C2 times e to the KLT out of the numerator and the denominator, which would leave us L on top, and then 1 over C2 times e to the negative KLT plus 1. Another pause here is recommended, just to go through the algebra, that is. And then let's rewrite this a little bit more, noticing that this piece here is a constant, so we get y equals L over 1 plus c e to the negative KLT, which is the solution to the logistic differential equation given by dy dt equals ky times L minus y. Let's look at the algebra one more time. We'll just start up here and I'll scroll down. We don't need to go through the steps. But look at all we had to do to get from our differential equation to our solution. So my recommendation to you is, whenever you see this differential equation, memorize its solution.